Okay, sir.
It's supposed to be 4, right?
Yeah, all 4 are here.
Oh, there's a 4. Okay, we got all of them. Thanks. Okay. So we finished last time at this table.
Hi, Professor, can you share your screen?
Oh, we have to share. Just a second. Share screen. And then go here and go here. Can you see it now?
Yes, Professor.
Yes, Professor.
Okay, so this was the table that gives you the boundary conditions or the terminal condition, or what we call them transversality condition for the adjoint variable for different terminal conditions on the state variable. You notice now that if you have a free endpoint problem, no, if you have a fixed endpoint problem, no, this is a free endpoint. This is a capital X. That means that the entire feasible set, my terminal state can be anywhere. So that's called a free endpoint problem. And in a free endpoint problem, the terminal condition is fixed. So lambda t is either this value, or if there is a salvage value, then the lambda t equal to 0. So because the derivative of that would be 0. On the other hand, if xt is a fixed, so xt is exactly equal to a point k, we call it a fixed endpoint problem. That means that if you want to get a 2-point boundary value problem, you have to give freedom to lambda t. So that gives you a 2-point boundary value problem. So lambda t is a beta, a constant to be determined. Here's an in-between case. So because it's an in-between case, the value of xt has to be bigger than equal to k. It's not exactly k. It's not all completely free. It is kind of half free and half not free. So because it's half free, half not free, remember we have a 2-point boundary value problem. So we have to let lambda t also half free, half not free. So the half and half, if you go Talmud way, half and half becomes 1, and so we have a 2-point boundary value problem in some sense. So that gives you the half a kind of a restriction on lambda t. Lambda t is bigger than certain thing, and it has to satisfy a complementary slackness condition. And if psi is 0, which is the salvage value, then you can see the lambda t is kind of half fixed. Okay. And similarly for less than equal to k, it's just the other way around. And that one is a more general condition. That means xt is a subset of xt. So xt should lie in a subset. So the subset could be that, could be that, could be that. So it is a general condition. If that is exactly equal to that, then so this fifth row cover 1, 2, 3, 4, all of them, it's covered by fifth row. And you can see that the condition for the fifth row is somewhat more general. And if you put this condition in the fifth row, you should be able to derive this fourth row. So from fifth row, you can derive the fourth row, okay? So if there are no more questions on this, we're going to solve the problem using half-fixed condition. Now, remember now, we already had this problem. We solved this problem when we fix the terminal wealth to be 0. And we fix the terminal wealth to be 0. That's a fixed endpoint problem, and we had a constant to be determined. So let's go back to that problem. So here is that problem. Here, wealth is fixed to be zero at the end. This person will like to consume, so he doesn't want to leave anything at the end. He wants to retire or die with zero wealth. Okay. Now, I put this only to make a connection with the next problem. This is a constant. It says this is the value of the bequest. But the bequest is zero. So this is the value of the zero bequest. It could be whatever it is. It could be zero, it could be one, it could be five, could be minus 10. Doesn't really matter. It is a constant. So you could actually remove that from the objective function. But if you don't remove it, then you have to add this back into, when you do the objective function, when you find the j, you see in the j I ended up this. I put this back in there. If that was not there, then I would not put it there. And the reason I did it is because I want to connect this to the next problem. Remember, I told you this problem is going to be running through the entire course. As we learn more and more things, we will try to generalize this problem more and more. And eventually in chapter 13, we will actually put some random stock market into there. So this problem will then be not only just consuming your wealth, but also investing your wealth. Okay, and the investment is a stochastic or a random process. And so we will have this problem will be more general problem later. So let's go to the next level where WT is bigger than or equal to 0. By the way, if there are any questions from the previous chapter, you can ask and we can do that. So now we have, you see, now we have b of the b of 0 was a function of 0, or not a function, it's a function of w, and the w was 0, so I just put 0 there. But now I'm going to specialize this function, b times 0, so that would be 0, okay? So now I'm going to specialize this function to b times w. That means every dollar you leave, your bequest value is b times that number of dollars. So if you leave WT dollar at the end, then your bequest will be equal to this. So in some sense, B is the strength with which you value, I mean, just figuratively speaking, if you value your children more, you will have a higher value of B. That means if you want to leave more money to them, you have to put more B because you have put more value. If you put more value to the bequest, then you're going to consume less. So you are actually sacrificing the current consumption to leave more money to your children or charity or whatever. So now we have a kind of a half-open terminal constraint, and we're going to solve this problem slightly differently. And the reason is that we can actually connect this problem to the previous problem. Remember, the previous problem is W2. Previous problem is I require the individual to fix, means don't leave any wealth at capital T. And because this is fixed, we left lambda T to be beta. The beta has to be determined. Well, the way we determine beta is so that this WT becomes 0. Look what happens. There's a beta. So the lambda T is terms of beta. Okay? Small t, I mean, this lambda, capital T is beta, lambda T is this. And now the optimal control is in terms of beta. So I can solve the problem with this control, with this consumption. I can find out the wealth with that consumption. But with that consumption, the wealth will also be function of beta. And I can put small t is big T, and then I make that equal to 0. Because what I'm trying to say is find me a beta so that my terminal wealth will be 0. That's what I'm trying to do here. So the beta gives you some sense the value, the shadow price of your terminal wealth in some sense. Okay. So now the beta has to be determined. So we put beta equal to 0 right here. We put W star T equal to 0, and then W star T equal to 0 gives you beta equal to this value. So the beta, of course, this is initial wealth, so it can depend on the initial wealth. So this is our value of beta. Think about this. If I go to this problem now, and I formulate the Hamiltonian, and I have a lambda dot, and now I have this half condition on lambda t, which says lambda t is bigger than b. I'm now using the table. I'm now using this condition of the table, row 3. So row 3, I have this and the complementary slackness condition. Notice what happens. You can easily argue that if I put a lot of value to my bequest, which means I put high enough value to b, then probably there is some b which will make me consume enough so that my wealth will be 0. No. Other way around. The b, if the b is sufficiently small, clearly 0. Suppose b is 0, the wealth will certainly be 0, because why would you want to leave anything? That's our previous problem. Okay? But if b is small, maybe not 0, but maybe a little bit closer to 0, you might still leave the wealth to 0. Okay? We don't know that, but there's a threshold value of b at which the wealth would be 0. Okay? And now notice that this condition actually gives us the threshold value. So lambda t has to be bigger than b. But remember, in our example, beta is exactly that in our previous example. So that beta actually gives me 0 wealth. So if that gives me 0 wealth, then any value, so, and beta has to be satisfied like this one. That means if b is small enough so that this beta is bigger than b, certainly this beta is positive, so certainly if b was 0, beta is bigger than 0, and this condition will be satisfied by the previous example. And the previous example gives us 0 wealth. So that says that all values of b that are less than this beta, then I would not leave any wealth. So beta in fact is the threshold of b. If b is less than beta, then I don't put too much value to the bequest. And if I don't put too much value to the bequest, it means I'm consuming everything. I leave nothing. So part 1 is solved. Part 1 says that this condition is satisfied. This condition is satisfied. How? Because if I if I put lambda equal to if I put lambda sorry if I put lambda t equal to beta, then beta is bigger than b, and wt is 0. So this is satisfied and this is satisfied. See, wt is 0 already. And it doesn't matter what the value, what is this difference? This difference is positive because beta is bigger than or equal to b, so it's 0 or positive. Regardless, this quantity will be 0. So 3.68 is satisfied. What I'm trying to say now is that in case 1, 3.68 is automatically satisfied if I set lambda t equal to beta. And so my previous problem gives me the solution. It's intuitive now. Now assume that b is too large. It's larger than beta. Well, if it's larger than beta, then notice what happens. If I put beta if I put beta in this denominator, then that W star becomes 0 at the end, right? So if I put, remember now the B, B is, go here. B is now bigger than beta. So it makes sense for me to replace this beta by B. Because I replace this beta by B, this quantity will not be exactly equal to W0, which will give me that 0. This quantity will be less, which means I will have some wealth left over. And bigger the value of B, smaller this quantity will be, and bigger W star T will be. What is it telling us? I can certainly put this B here, whatever that B is, and it will automatically give me the wealth that I want. So that's exactly what I'm going to do. So in case 2, we just set lambda t equal to B. If you set equal to B, then our lambda t is B times that, not beta times that, but B times that. Then our C star t will be a little bit less, because instead of 1 by beta is 1 by B, and B is bigger than beta. So our C star t will be a little bit less than the previous example. And if it's a little bit less, because previous example had just enough C star t that gave you the wealth at capital T to be 0. But now I'm consuming a little less, and whatever that consumption is, it will leave me the wealth, whatever wealth it will leave me. So what I'm trying to now say is that when in case 2, when B is sufficiently large, then I set lambda t equal to B. If I set lambda t equal to B, then I have a 2-point boundary value problem with B, and whatever WT I get is the WT I get, because that's free. It's free as long as it's about 0. And so if you set lambda t equal to B, then W star t will be bigger than equal to 0. But lambda t, now that difference would be 0, because I set lambda t equal to B, so that difference becomes 0. And this can be whatever it can be. So this product is still 0, and 3.68 is satisfied. So notice, one WT is kind of half free. Then by some argument, we were able to determine a lambda t threshold value, and now we can set B, which is bigger than the threshold. We set that exactly equal to B, and that condition tells us that's what we have to do. Because if we set anything bigger than B, then this is not 0, and then that condition will not be satisfied, because that's not 0 anymore. So we need this to be 0. And the only way to make this to be 0 is to set lambda t equal to B. That's how you resolve. So that complementary slackness condition leaves you no room for freedom. It basically, it is a boundary condition that exactly determines the solution. Otherwise, this boundary value problem is overdetermined, and we have no way to deal with that anyway. So now we have W star t equal to this, and we can compute W star capital T exactly is this, and which is definitely bigger than 0. Notice we used table 3.1 row 3. But we could also use, table is derived from maximum principle. Well, we can always go back to maximum principle. And the maximum principle has something called alpha. So basically that lambda t in maximum principle is just b plus alpha, and alpha satisfies the complementary slackness condition because alpha is exactly this value, lambda t minus b. So let's go to 3.42 just to look at it. You see what's going on here? Beta is now beta plus alpha. There's a beta here, and there's alpha here. That's one. That's one. And so we have alpha bigger than 0. There is not that's exactly b. That's b psi x. Remember, psi x is the psi x is the salvage value. Salvage value is b times w. So w is the state variable x. So psi b would be exactly, psi w will be exactly b. So this is b, and those conditions are um, that's b, and this is alpha. That's 0 because the condition is wt bigger. So only a constraints are there. So a sub x is 1 because a bigger than or equal to 0 is wt bigger than 0. So wt bigger than 0 will give you 1, and that gives you alpha. So it's b plus alpha. And b sub x, there's no equality condition at the end anymore. So this is 0, so we don't have that anymore. Equality condition leaves this out, and we just get this beta. So you see this condition gives you free endpoint problem. The fixed endpoint lands you here, and half free endpoint lands you there. Give me 1 second. Okay, I'm coming back to, sorry, I need to do certain things. Yeah, can you see this? Can you see this?
Yes,
Yes, we
Professor.
can.
Yeah, you can. I'm sorry about that. I just got a critical email. We have decided whom to make an offer to. And so I wanted to read it to see if I need to do something right away. But I'm the last to sign, so I can do that after the class. So any question on Achusha wanted to ask questions about terminal condition. Do you have a little bit of a more understanding now of the terminal condition?
Yes, I did. Thank you,
Okay,
Professor.
thank you. Thank you. Let's now look at a problem that we're going to solve using 3.42. This is also a condition in which the final terminal condition is bigger than or equal to 0. So we're going to have another problem. But the reason I want to give you this problem is I also want to give you a little bit more on the value, the marginal value interpretation of lambda. Okay, so that would be an extension of this example. So we will first solve this problem, and then we'll continue. So this problem is similar to the one that we had before, but now we had the problem before, but right now I put a condition that x2 is bigger than or equal to 0. Same, u is between -1 and +1. We still minimize the area under the curve, which means maximize the minus of the area under the curve. And we have h equal to minus x plus lambda u star is bang minus 1 lambda, and lambda dot equal to 1, and condition from 3.42 is lambda 2 bigger than 0, lambda 2 times x2 equal to 0. We know that, so, once you apply the maximum principle, then how you solve the problem is not always, mechanical. That means you sometimes um, use some intuition to move you along. But if you want to do algorithmically, you can actually ask the computer to solve this problem, and but computers sometimes you will have to solve the 2-point boundary value condition. This is more complicated than the Excel program that we had in chapter 2 to solve that problem. I'm not doing anything more than that anyway computationally. So if you want more sophisticated computational software that can solve more complicated problems, there's enough in the literature to do that. So from here on, other than one more time, maybe give you an Excel solution or problem. But other than that, our job now is to try to find as much as possible explicit solutions or solutions that we can say something about. Okay? That's what the research is all about in most of the control theory papers. If you just do this and give a computer algorithm to solve it, that's not going to give you a publication paper anyway. But if you do something more and find something interesting, then that gives you, for example, recently, um, um, or you can have a very complicated problem which has no explicit solution. You can solve numerically, and then you can do different parameters and solve many different cases. And from these, you try to gain some insight. That's another way. We recently published a paper in POM that actually just came out a couple of months ago. And that is also cited in the book as a forthcoming paper at the very end. That is a big problem about the pandemic and the controls, optimal control of a pandemic. We don't do vaccination in there because the problem was formulated before vaccination, but it's still a large paper that just got published in POM. So that's another way. So there are different ways I'm certainly keeping publishing papers on optimal control even at this late day. A few more in works and under review right now. Okay, so there we go. Lambda dot 1 means lambda is going to increase monotonically. And if it's going to increase monotonically, then 3.72 says that the control can switch only from, because when lambda is positive, the control is 1. When lambda is negative, the control is 0. The control is minus 1. So, and since lambda is going increasingly monotonically, it can either be all positive, in which case the control will be 1 all the time, or it can be negative and then becoming positive, in which case the control will be minus 1. Lambda is going to increase from negative to positive. At some point, it will be 0, which will be a singular point at which we can do whatever we want at one point. And then it goes to, the control switches from minus 1 to plus 1 at that point. So that's the insight we get already from these guys, okay? Now, with this insight, we are going to go and try to solve the problem. So the control can switch only from minus 1 to plus 1. So what we can do is we can say, okay, let it switch at some time t star. Well, the switching cannot be after 2 because our end time is 2. So whatever the switching time is, it has to be less than equal to 2. If the switching time is less than equal to 2, then according to the bang bang principle, lambda u star is minus 1 up to t star and is plus 1 after t star. Okay? So we know that. We also know that at T star, lambda is going to go from minus to plus. And this is a continuous lambda. All lambdas are continuous up to chapter 3. Chapter 4 is more complicated because lambda itself can become discontinuous. And that is one of the biggest hurdles in solving control problems. And that's why chapter 4 is the last theory paper chapter that we're gonna discuss. So we know the lambda dot 1 means lambda, the solution of lambda, the general solution of lambda is t plus a constant. So if you integrate that, solution will be t plus a constant. So t we know, the constant we don't. But we know this, lambda at t star has to be 0. And the only way, so the constant is exactly minus t star. Because lambda t is t minus t star. So at t equal to t star, it becomes 0. So we already got the constant. So we know the constant is this switching time. Of course, we don't know the value of it, but that is our constant. So here, constant can be anything when you solve this problem. It's just t plus a constant k. But that constant k, given all the arguments so far, we know that constant has to be minus t star. Where t star is exactly the point at which lambda will switch. So now what do we do? Well, we know this, so we can solve the problem. We can solve for our state. The state is xt, which is, so there are at this point I want to say a little bit more because remember t star is less than or equal to 2. So there are two cases. One is t star strictly less than 2, and one is t star equal to 2. There are two cases. If t star is equal to 2, then the control is going to be -1 all the way to 2, and then it switches exactly at 2, and at 2 you can do whatever you want. It's just one instant. The problem is over. So the +1 never gets a chance to go any further. You can set +1 at that t equal to 2, or you can set 0 at t equal to 2. You can set whatever value you want at t equal to 2, t equal to 2 at that point. And so that's one case. The other case is the t star is strictly less than 2, in which case there will be actual switching. So let's look at that. Let's look at these two cases, and let's solve the first case first. In case 1, now lambda 2, by our formula t minus t star, lambda 2 will be 2 minus t star. And since t star is less than 2, 2 minus t star is bigger than 0. If lambda 2 is bigger than 0, then our condition of transversality says that x2 has to be equal to 0. So we have x2 equal to 0. Now we solve xt. Well, xt is 1 minus t up to t star, because xt, look at the picture here. You go over 1, and you're using the control -1. So this thing is going to go at the slope of 1, and it's going to become 0 here. And this is your t star. So it will continue to t star. We will see what the value is right now. We don't know the value yet. It'll go up to here. Then it will switch to +1. It will start increasing. But if you want to make it that x2 is 0, and by setting x2 equal to 0, you will find what t star would be. Because if you go like this, you can go like this and go like this. You can go like this and go like this. If you go a little bit early, then it'll go like this, and x2 will now be 0. So you can sort of see what's going on. So this is 1 minus t, and then xt beyond that t star is going to be whatever the value xt star is, and then you switch the control to +1, and you get the value t +1 minus 2t star. So you can solve that xt. So the xt in a picture is this and then that. We don't know the t star yet, but it's that and that. But the only way x2 can be 0 is if I put t equal to 2 and set it equal to 0. So I put t equal to 2 here and set x2 equal to 0. When I put t equal to 2, x2 would be 3, which is 2 plus 1, 3, minus 2t star equal to 0. And that gives me t star equal to 1.5. Notice now, if I do all of that, everything is satisfied. Maximum principle is satisfied. So I don't have to go to case 2 altogether. We don't need the case 2 anymore. Let me continue further. So xt star with t star equal to 1.5 is given by these formulas. And the value of j star is given by minus 1.4 because you can integrate this business and you get minus 1.4. Now look what's going on. Here's our picture. xt goes like this, and then it goes like this. Lambda, on the other hand, starts from here, goes to 0 at t equal to t star, and then it goes to half at this point. And all of that gives us t star equal to 1.5. Notice that this one gives us this, but suppose x was quite far above. So if it was like here, just a little bit above here, we can still do that. We can go here and then go there. We will, of course, have to determine the new value of t star because we will go like this and go like this. But at some point, you will see that that curve, that point will be this point. So if you go all the way up to here, this is your x, then x will only go all the way up to here, and you hit 2 and exactly at 0. At that point, both this case and this case combine. They are the same case. Whether you do this or do this is the same, because that will give you t star. Well, it is this case, but if you can see that case t star less than 2 is just before that. Okay. And if x is even beyond that, then control is going to be always minus 1, and you're going to end up at a value which is bigger than 0. And that would be exactly this case, because this case means there is no switching anywhere, and whatever the initial value of x is, it will give you some value of x star t, x star capital T or capital 2, give you some value which could be anywhere along at value 2, x could be anywhere here, depending on where you begin with. If you begin with 3000, then the value here will be 3000 minus 2. Because 3000, x is 3000, it goes down with the rate 1, control never switches. So in two time period, it only decreased by 2. So x, the trajectory will go from there all the way up to here, and this value will be 3000 minus 2. Notice that if x is very, very small, and even if you put x equal to 1, x2 will never get to 0. x2 can only go to 0 up to this value of x. If you go back all the way here, that value of x is the last value for which the problem is feasible. Below this curve that I extend here, if I give you initial condition anywhere here, it's not feasible. And if it's not feasible, then the maximum value of the objective function can be said to be minus infinity, because there's no feasible solution. So you can call it minus infinity if you want. There doesn't exist any solution which is feasible. So there is no really an optimal control problem. But whatever control you will put, will not give you 2, whatever feasible control, because feasible control has to be between -1 plus 1, and you cannot do more than 1. So you can only rise at a certain slope, which is a slope of 1. So if you're very far below some value of x, then you can never get to 0. So with these kind of remark, we'll go to the next place. We will now want to show that this lambda t that we got, which is now t minus 3 divided by 2, is t minus 1.5. Lambda t now is t minus 1, t minus 3 by 3, that lambda t is right here, t minus 3 by 2. This has this value that if I give you a little bit more x, then if I give you epsilon more x, then my objective function will change by t minus 3 divided by 2 times epsilon. If it's 0, if I give you the x, so what I'm trying to say is that if I give you 1 plus epsilon, I think we did already that in the previous setting. If I give you 1 plus epsilon, then the trajectory will be just parallel to that, about epsilon here. Then it will go like this here, and then it will eventually go there. Okay, so it'll go up to this point and then go up to there. Okay, so this t star will be slightly bigger than 3 divided by 2, and you can find the new value of the objective function. The new value of the objective function will be lambda times epsilon. But notice the value function is a function of x and t. So it allows you not just to vary x at time 0, it allows you to vary x at any time t. So this is what we're trying to do now. So this is an example which is, you will not find some stuff like that in any other book. So my book was nominated for Lanchester Prize for Exposition Award, but didn't get it. Maybe another time we have to apply for it. But apparently somebody thought enough of this to nominate this for exposition. So after 4 editions, it has become better and better. So now we want to find the marginal value of lambda. And for that, we want to find the value function. The value function is this. So value function says that if I begin with initial condition x, and I begin with some time t, which doesn't have to be 0, then I solve the problem for that t all the way to 2, which is the terminal time at this point. And from that value of x, I solve a new optimal control problem that begins with a t. Now, remember now, we have not formulated a problem in chapter 1 and 2 that begin with t. So all our problem go from 0 to some time capital T. So if I give you a problem from t to 2, well, all you can do is you define a new time tau. The new time tau will be 0 at small t. Okay, so you can define tau equal to s minus t, and so your equation then in terms of s and tau equal to 0. So all the equations will be in terms of s. S is your new time, changing time, and so you can actually do that and resolve the problem as if it was a chapter 1, chapter 2 problem. And then you get the optimal control for that problem. And that optimal control problem give you this value Vxt. And what we want to show now, that if this Vxt is differentiable in x, then its derivative should be equal to lambda. But that is the marginal value of x. That is the best I can do from going from time t to 2 with initial value of x. That's the best I can do. Then if I take the derivative, it gives me the marginal value of x, or the state. That's what I want to demonstrate now. Now, in order for me to do it so that I don't spend too much time in class, I do only part of it. So the part I do is this. First of all, we want x2 to be bigger than 0. So we only want to deal with xt that are feasible right now, because if it's not feasible, this is minus infinity. So what I'm trying to say is, I gave you the example. If x is somewhere here at 0, if it's here, it will never go to 0. But at any other time t, if it is below that line, I can never get there. So x bigger than or equal to t minus 2 has to be the case for any value of t. So for any given value t, my x initial condition has to be bigger than t minus 2. Otherwise, I won't have a feasible solution. So let's only deal with the feasible solution right now, because only when the feasible solution I can find a vxt. Otherwise, I set vxt equal to minus infinity. Okay. So now I need to obtain the value function xt by solving a control problem that begins with a t with a value of x, which has to be bigger than t minus 2, and it goes up to 2. So xt equal to x, and that is our time t. That's our initial time now. So I need to find a s, which is the time that goes from t to 2. I need to find that time, okay? So this is my s. But s can only go from t to 2. Okay, so it goes from t up to 2. You see that? But if I want to change that time to tau and call tau to be s minus t, then tau will go from 0 to t minus 2. And then you can solve the problem. And once you solve the problem, you get a control. Optimal control, then you can optimal state. Once you get the optimal state, you can put the optimal state into this objective function here and find the value j, and that j is exactly vxt. Now, how did I write this solution? Well, I just did the following. I went here, and I know that whatever I do, if my x is not too high, then I will go here, and then go there. So somewhere I will switch, and I'll go there. You notice what is going on? Because going down is -1, going up is +1, then if I go down to a certain value, and then I use the +1, it will take the same amount of time to go. So if it took so much time to go to here, then the same amount of time will be taken to go back to 0, because the other side is +1. If it's +2, it'll be a different calculation. Okay, so I know this kind of picture that's going to give me an optimal solution. So I don't have to go all the way to the first principle and apply the maximum principle, change the time to different time and solve the problem. I can do it, but it's not going to be there. So a few minutes before I was in a class, I decided to show you how I got this control. The notation is the same as the notation 2.5, example 2.5. This is not an extension of a 2.5 problem. Notation is the same. So the notation says u star at time s, where s goes from t to 2, u star of s at time s, given that we began at time t at value x, the optimal control of that is -1 for this value of s and a +1 for this value of s. So it's -1 for a while, then it goes to +1. And how do I determine that? Well, I determine that like this. Can you see this? Can everybody
Yes,
see that?
Professor. Yeah,
Huh?
I can see.
Yes.
Yeah.
Okay, so you can see I have x. So this is my t, and this is my x. And this is my 0, this is my 2. I'm not changing the time. You can change the time, go back, and eventually you will get this formula. But by using this picture, we can directly go to this formula. So if I want to find an optimal control according to this idea that we have, then I will use -1 all the way up to here, goes to 0. Then somehow I will go all the way here and go far enough, not too far and not too little, not too much. I will go up to here so that when I change to +1, I get up to back to here. The only way to do that is if this point is right in the middle of those two. That point is t plus x, because this is t, this is x. So going with a rate of -1, it will take me x amount of time to get to 0. So this time is t plus x. And this time is 2. And this time is halfway between 2 and this. Well, how do we get halfway? This is my S star, because now my S goes from here to there. S goes from t to 2 minus t. Okay. No, S goes from t to 2. Sorry. So now S star is halfway. What is halfway? Well, halfway is t plus x, which is t plus x plus half of this difference. So I add this amount to t plus x. This amount is exactly 1 divided by 2, and the difference is 2 minus t plus x. So that difference, 2 minus t plus x, is this whole thing, and half of that is half of this whole thing, and I add that half to t plus x. So this t plus x, and I add this, I get s star. I simplify this, I get the value of s star. Okay, that exactly is S star right here. This is the S star. So I go from T, S goes from T to S star, and then S goes from S star to 2. I get my control. Once I get my control, I obviously can solve for my state. So that is easy to do. This is the integral. When I have this, I put that in objective function. And remember now, this is for x bigger than t minus 2. So I put an objective function. First, I integrate from t to 2 all the way. Integration of t of 2 require two component. One is from t to this s star, and one from s star to 2. From t to s star, I put this value, this value, and from s star to t, I put this value. So I put these two values, I integrate, I solve, and notice for xt minus 2, there is no feasible solution, so vxt is minus infinity. But for this value, now we verify that for 0 to t, now I want to tell you this. This problem is being solved only for not all of the values of t. I'll tell you why I'm doing that. I'm only going to do it for up to 3 divided by 2, because in this case, I can find x star t, and I can find the vxt. So v of x star t, which is the lambda t, and take the derivative of that and put x star t in there. I do that, and I get t minus 3 by 2, which is exactly lambda t. So I've demonstrated that lambda t, in fact, is the derivative of the value function when value function is differentiable. If it's not differentiable, there are other ways to deal with this, but right now we are not going to do that. But I do want to mention to you, so what do I do with this? Well, my secretary forgot to put the slides on that. And so these slides would have to come another day, but I will go to the book. And so there are two ways to do it. We can either, you can have your own book and we can just go there, or I can go to my book and then I can show it to you. So let me stop presenting, then go to my book. Let me open the book. So open the book, and then I'm going to go back and share the screen again. And here's the book. You see now?
Yes, Professor.
Okay, so you see what we just finished up to here. Now what happens when t is below 3 by 2? No, above 3 by 2. In this open interval 3 by 2 to 2. Clearly, for x bigger than x star t, we may still use all of this. So the right hand derivative would still will be, in this case, would be 0. You can do this calculation at home if you want. However, for x less than x star t, there is no feasible solution, and so v of this is minus infinity. So what I'm trying to say is that in these cases, the value function is not differentiable because one side it is this and the other side it is this. For value of x, for x above the optimal solution, optimal trajectory, I have this derivative, and below I have this derivative. So on the left and the right hand derivatives are different. So v sub x does not exist. Value function is not differentiable. And so lambda t, whatever lambda t we get, it's going to be a discontinuous, not discontinuous, but it's going to be not obtainable from the derivative of the v sub x because v sub x is not differentiable at this point. Okay, so that could be a slide that we didn't have to go back to this. Any questions before I go back to the slide? But generally speaking, this is good enough. This is just not necessary to present. You can just go and say do it yourself. Okay, I'm going to go back to getting better at this. Stop presenting and then share again and go here. The next thing you want to do is to give you some idea of this condition. If t itself is a decision variable, and which, by the way, are many problems. In fact, some of my early publication was machine replacement problem, where you maintain the machine, and we will actually chapter 9 we will go over that problem. That is a problem where you have to find out the time at which you should sell the machine. And that is optimal time, because if you sell too early, it's expensive. If you sell too late, it's expensive. So you have to find the optimal time to replace the machine. That paper that I cover there in chapter 9 is a paper that was published in Management Science, and we will cover that in chapter 9. But right now, we're going to use this condition in chapter 9. But this condition looks very ugly. It doesn't tell you anything. You know, so what? Hamiltonian is and this equal to 0. So what? So we want to put some teeth into it. Okay, so let's do that. And this is an intuitive way of doing it. One way of doing it. But the other way of doing it is like this. There's a paper by myself and one of my postdocs that basically says this, which is a very simple way to think about it. What you do is you fix t. You fix t and you find the optimal solution. Then you integrate that optimal solution and find the objective function. The objective function will be a function of the fixed t, because t you fixed. So objective function will be can be given as a j star of t. So it's only a function of one variable, and now I use the calculus. I take the derivative of that with respect to t and set it to 0. That's called the first order condition. And that should give me, if I do that, that should give me this condition. Now, I only want to tell you this. This is easy to explain, but to take that derivative is not easy, because we are not able to explicitly. For any given problem, exercise. You can do it. You can explicitly solve the problem and find the j star t as a function, take the derivative, set it to 0 and solve for t. That's easy. But for a general problem listed in chapter 2, chapter 3, that function is not something that's got a lot of integrals and lots of things going on. So you need to find its derivative. And once you find its derivative, you have to now to show that this condition reduces to this condition. So that's the difficult part. So easy part is what this t means, how you can obtain that t. This is very easy to, this goes back to calculus, so everybody can understand it. But once you get there, how to get this it's a difficult step. This difficult step. So if you want to go through that, this is just a short paper that you can easily find in the literature, and you can look at this and see how we derive this problem. By the way, you don't find this proof in any other places easily, because this proof can be done in a different ways, and so no one ever thought of writing this way. So we were able to publish that, and I think that, in my own view, this is more important paper than a credit is given to this paper. Let's put it this way. Maybe it was published in a journal that was not as popular as management science. Okay. So what we're going to do is an intuitive explanation of this, and which goes like this. So let's assume that we have a T star that satisfies this condition. But if it satisfies this condition, then any t in T star to T star plus delta, which is not T star, should give me a lower value of the objective function. So if I change the T star a little bit, if I increase the T star a little bit, I should get not a good value of the objective function. I should get a lower value of the objective function. If I decrease the T star a little bit, when I said T bigger than T star and smaller than T star plus delta, I actually mean that you solve the problem for this new T. When you solve the problem for this new T and compute the objective function, that objective function will be less than objective function with T star. If you decrease T star by a little, once again, the objective function value should be less than the value at T star. So for any value of T in T star minus delta to T star plus delta, I should be able to show that locally T star is optimal. If I increase, I suffer. If I decrease, I suffer. Okay. Now, rather than solving this problem, I only want to solve you to show what I just argued. So what I'm going to do is because this is small order delta, so delta is small, and I can take limits. I can make a small order delta, so I can make some approximation, and so I don't have to be exactly optimal. So here's what I'm going to do. If it's T star minus delta, I already know the optimal control all the way to T star. But if it's above T star, I don't know what the optimal value is unless I solve the problem again. And then that goes back to the Hartle-Sethi approach in 1983. What I'm going to do is I'm going to say in that interval, which is slightly above T star, in that interval, I'm going to use the same control that I had at T star. So I had whatever control I had like this, that one I'm going to just go like that, constant from T star to T star plus delta, exactly at this value. That means U star is continuous, the new star, the modified is continuous. And I can then find the trajectory, the corresponding trajectory for that control. And that certainly is differentiable because the u star, this is integral. You get integral of the control to get the trajectory. So I have a differentiable trajectory. So Jt now is defined to be any value from 0 to t of that control I just fudged in this interval. So if I choose the t between this and this, and I set this control from t star to t star plus delta, I get j of t. I can define it this way. So that's step one. U star is continuous. X star is continuously differentiable. So since t star is optimal, then a derivative of this with respect to t at t star should be equal to 0. I can take the derivative because of all of this. Well, if that should be 0. If not, then we would either have j prime t star bigger than 0 or j prime star less than 0. Let's say it is bigger than 0. It's bigger than 0. That means that the former solution would allow us to find a t for which jt is bigger than jt star. The former situation, this situation, will allow us so that happens. And so T star could not be optimal, since the choice of an optimal control for 2.4 defined on the interval 0 t would only improve the value of the object function. Likewise, the latter situation would allow us to find a T star in this interval for which JT is bigger than JT star. So this kind of intuitive reasoning allows us to say that these two cannot happen at T star. Because if that can happen, I could do better. That's all it says. So I'm going to take the derivative of JT, which is this guy, because this is well defined. Once I define this U star T star from this interval, this is well defined for every T in this interval. So in that interval, I take its derivative. And this is an easy derivative. It's a derivative inside the integral. So I take J prime T. And you can see that derivative will be F. The first part is F. The second part is S sub x, which is S sub x. And once you take S sub x, then you take the derivative of x with respect to t. So x star dot t star. So that's the part coming from there. And part coming from here is this guy. So we got this. Notice that one is F. That one is lambda t. Lambda t is S sub x. And that is exactly F. X dot equal to F. So F plus lambda times F is Hamiltonian. That's exactly this. And that second part is exactly this. So this is exactly 3.77. So this now it makes a little bit more sense to you why this condition is the condition that we impose on T star to find the optimal T star. Any question here? This is reasonably, I mean, it's a sufficiently rigorous proof. Once you have that, there are problems and exercises where we give you what if I must find a t star between this interval t1, t2? Well, then that is basically a calculus problem again with constraint. So you set this equal to 0 if the optimal solution is interior to this interval, which is this case. If it is less than 0, then you set this quantity, your t1. And if it's bigger than 0, you set that. This is like the SAT function. If it's above the range, you get this one. If it's another range, you get this one. And so this condition now, 3.77, can be generalized to 3.81 if this is the case. This is straightforward. Once we get to this point, this is a straightforward extension. And so we can actually write this condition as a condition if we are asked to. Notice, for example, even though I didn't tell you this t here is already constrained on one side. So if you got this condition and you can never satisfy this, then you have to set t star equal to 0, but that's not a problem anymore, right? That's why I don't bother with this, because if the optimal t star is 0, then there is no problem because there's no time to go anywhere. So that is a pathological problem, which we don't have to worry about. That's why I don't bother with this. So this is kind of implicit, but this could be 0 and that could be T2, in which case certainly this condition can still be applied. So here's our first example to show this application of this condition. So let's do that. See, we're getting slightly more complicated problems now. This problem, it's not so easy to give a guess. So you know what I mean is, like, you could argue that this particular problem that we solve, well, I mean, I could just heuristically give that solution. I can guess the optimal solution, but guessing is not proving it. So in these cases, you can argue that I don't really, if I'm an anti-vaxxer, I don't have to prove it. I just give you a solution and you just agree with me that that is an optimal solution. But if you want a proof, the maximum principle gives you the proof. So you can guess first and then prove first. So that's what we've been doing almost all, except one problem in chapter 2, where we had a SAT function. Most of the problem that we have done so far are problems where we can more or less guess a solution. Or maybe consumption problem, we may not be able to guess the solution, but many other we could. So I don't want to have an impression that the only time we can solve the control problem is when you can guess it. Guessing always helps, but it should be more than that. So we slowly are getting problems where we cannot guess the solution, okay? And we can still use the maximum principle to solve the problem. So here we're going to do, we do not know exactly what is the optimal T star here. We actually also don't know what the optimal control is here. We really don't know. By looking at this problem, I cannot guess anything. I certainly cannot guess anything. So let's solve this problem. Now this one is more or less, maybe I should have given this problem also in chapter 2 without this condition. And I can still solve the problem, and it will be a problem that is not guessable. Okay. So here's my Hamiltonian. Here's my lambda t. Here's my bang control. But remember, the bang control is now in terms of t. And u star is 1 up to t minus 1 and is 0 after that. Solution is still very simple. 1 up to t minus 1 and 0 after that. You see, you couldn't even, it's a very simple solution, but I could not tell you So that would be the solution of this problem. It basically says go 1 and then go to 0 just one time before the final time. But that's half the problem now. We still need to find T star. So we know that if we do that, then U star T star is equal to 0. Right? So we can, because remember we need this. We need this quantity. We need this quantity in the Hamiltonian. You see here, we need this. We need this. We need this. We have that. So we go there. We have lambda T star. So we put all those values. Huh? You got it. We got a minor typo here. Is that also in the book? Is there a T star in the book? Huh? I thought this book is error free, but you never know. I'm looking. Oh, book is not a mistake. Good. Slide is a mistake. The slide, this should be T star. The book doesn't give you this. It just satisfies everything and gives you only this. So I'm glad. I mean, the book doesn't have to be changed. Slide. From.it always blocks my, okay, slide 82. Slide 82. 3.85. Now the T star. Okay, sorry. So we have this equal to 0. But we can solve for x star T star because we know U. So we put U and we solve for x star T. Up to T minus 1, control is 1. After that, control is 0. So we can easily solve that. When we solve that, we can find x star of T star, which we can find out right here. This is x star of T star. So you put T star there. And then you put minus 2 and put it equal to 0. So I have a 17 minus, oh yeah, because this is 2T star. 2T star minus 0.5 is minus 1.5 T star. You get it? I'm applying this condition. I'm putting T equal to T star. So I have a because I'm trying to find this value at T star, and suddenly this will be T star also. So this becomes T star, this becomes T star. So the difference of that becomes minus 1 T star, 17 remains 17, and 2 is coming from here. So applying 3.85, I get this equal to 0. This is the equation in T star, which I can solve. So T star comes 10, and my optimal solution then is T star is 10, and U star is 1 up to 9, and 0 from 9 to 10. Okay. Any question there? So this is a very nice little problem that has a simple solution, and it demonstrates quite a few things, right? It demonstrates the power of maximum principle one more time, and it also gives you the terminal condition that gives you an optimal time t. At this point, we're going to take a break. The next problem is one of the classical problem in optimal control. And I will spend a little bit more time in explaining that problem. So let me take 5 or 10 minutes break, and then we will come back, okay? Because this is a problem that requires some, it's a problem which is very, very cute problem in some way. And it also has 2 variables instead of 1. And it allows us to solve the problem. It also tells you that an equation like this can still be dealt with because this is double dot, but we can still deal with such equation and still reformulate as an optimal control problems and then pretty much solve it. I also want to tell you that it is this kind of problem, exactly this kind of problem, that allowed the first landing on the moon. The first landing on the moon basically was solved by optimal control problem. It was an optimal control problem, which I understand had 6 variables, not 2, but 6. And it was solved, of course, numerically by optimal control software. And that allows you to tell you how to accelerate the rocket, where to this, where to do that. It takes into account the gravitational force of the Earth and the moon and all of that. And then that becomes somewhat complicated. But it is this problem, more or less, that is responsible for the first journey to the moon. And so in some sense, it's an interesting problem to look at, okay? So let's do that. I'm going to, no, there's no reason to stop presenting. I'm just going to leave it here, okay?